Hello, everybody. Hope everybody had a nice lunch and had enough time to grab a coffee. And to accompany that coffee, we have Savas Katanakis, who is going to be presenting investigating location-aware advertisements in Anycast IP networks. And with that, Savas, the room is yours.
Thank you very much. I can hear myself, but I can fix that. So
we hear you.
Hello.
Well.
Okay. The problem is that I can hear myself, but I'll just volume down a little bit. Okay. So hello, everyone. My name is Savas Kastanakis, and I'm a PhD candidate in Lancaster University under the supervision of Professor Niraj Suri and Dr. Vasilios Giotsas. This is a joint work with Dr. Ioanna Livadariou from Simulamed, in which we investigate location-aware advertisements in Anycast IP networks. Over the last 4 years, we focused our research on trying to improve the well-known poor predictability of interdomain routing simulations. So in our first work, published in IMC 22, we identified and quantified the confounding factors that prevent us from conducting high-fidelity simulations. Among those factors, we pinpointed two things: the complex routing policies that autonomous systems configure and deploy on the interdomain routing system, as well as the geolocation-agnostic BGP best path selection process. A year ago, we studied the first confounding factor, which is the actual routing policies of autonomous systems on the internet. And in that work, published in IMC 2023, we observed that currently ASs do not configure their routing policies based on the business relationships with their neighbors, which is an assumption that holds in controlled experiments and simulations, but they prefer more expensive routes based on their performance, security, or traffic engineering goals. In this work, we focus on the second important confounding factor that we identified, which is the geolocation-agnostic BGP best path selection process, and we study the prevalence of regional trends and selective announcements in Anycast IP networks. So, Anycast is one of the fundamental modes of communication in which a set of Anycast replicas, also known as point of presence or POPs, all serve the same content under a shared identifier. In IP Anycast in particular, POPs at multiple geographic locations advertise the same IP address using the Border Gateway Protocol, and clients are routed to a replica or POP based on the underlying BGP routes. And from the client's perspective, all of these POPs offer equivalent services. Now, what makes IP Anycast attractive when deploying a globally replicated service is the mental model that it seems to permit. In particular, as a network operator, as an autonomous system adds more Anycast replicas in locations with many clients, it is believed that the overall client latency will decrease and load from nearby clients will be evenly distributed across the POPs. As an example, the blue Anycast network in the bottom of the figure that you see has replicated its content to 3 POPs, one in America, one in Europe, and one in Asia. And if everything was working based on our mental model of Anycast routing, then the orange user would be directed to the orange POP, the purple user to the purple POP, and the green user to the green POP. As we said, though, Anycast routing depends in practice on the Border Gateway Protocol, or BGP, to advertise the same prefix from all POPs to the rest of the autonomous systems on the internet. However, BGP is not guaranteed to be optimal in terms of bandwidth, latency, or geographic proximity. In the best case scenario, BGP can be relied for connectivity, reachability, and policy compliance. And although user-to-site mapping generally follows geography, prior studies have shown that the actual network topology can vary, and recent observations have shown that the mapping depends heavily on the policies of many networks on the interdomain routing system, thus it can be unexpectedly chaotic. And unfortunately, other prior studies have shown that IP Anycast performance does not match even the most basic expectations of network operators, since clients are often routed hundreds of kilometers away from the closest replicas, resulting in increased latency, which is counterintuitive with the paradigm of Anycast routing. And it has been known for over a decade, approximately 15 years, that IP Anycast can be inefficient, yet there are surprisingly few explanations of why or how to fix it. But these explanations include the complex routing policies of the networks, the geolocation of the replicas, and the traffic load of those POPs, those replicas. Now, to make things a little bit more complex, an autonomous system, either Anycast or Unicast, might select to restrict the propagation of certain routes for traffic engineering and load balancing reasons. This phenomenon is called selective announcements. In the Anycast use case specifically, an Anycast AS might strategically employ selective announcements because they want to load balance their traffic and costs to certain POPs based on their location. We have currently identified two types of selective announcements: selective announcements per autonomous system and selective announcements per location, in which a network might selectively advertise their prefixes to a subset of its neighbors or to a subset of its POPs based on their location respectively. Nonetheless, in this work, we focus only on the second type of selective announcements. And specifically, what we try to do here is, first of all, to measure the adoption of the selective announcement phenomenon across Anycast ASs, to identify the receivers of those selective announcements, and then to measure the regionality of those receivers, or in other words, the degree at which those receivers are either regional or global networks. Now, the results of our work, even though preliminary, underscore the necessity to take geolocation into consideration when we model the interdomain routing system, so that we go to a more BGP-aware, geolocation-aware BGP-based path selection process. Now, I won't stay a lot in this slide. It's our methodology overview. We'll dive into the details of the methodology later on, but what I want you to see here is that we mainly identify the Anycast ASs and the prefixes that they advertise to the rest of the internet. We infer which of those prefixes are selectively announced to a subset of the Anycast origin neighbors. And finally, we geolocate this subset of neighbors, the receivers as we call them, in an effort to try and capture and uncover regional trends in Anycast routing, so that we can later on use these regional trends and embody them in our simulations and refine the accuracy of the simulations. Now, the first step is a pretty straightforward step. What we do here is that we map Anycast prefixes to the Anycast origins, and we leverage the BGP Tools API and the BGP Tools GitHub repository to make this map. Actually, it's a dictionary that you can see on the right of the screen. The keys of the dictionary are the AS numbers of the Anycast ASs, and the values are the Anycast prefixes originated by the respective network. Now, in the second step, we use the BGP Stream API to collect the routing tables of all the vantage points that are available in the RIPRIS and RouteViews projects on the 1st of November in 2023. Now, these tools, these platforms are BGP data collection tools distributed across the globe. But from the BGP data that those tools collect, we only care about the bold things that you see in the box, about the prefix and the AS path to that prefix. For those of you who don't know what an AS path is, it's a sequence of networks, a sequence of ASs that are going to be traversed from a source autonomous system to a destination autonomous system and a destination prefix, respectively. And since this study is focused on Anycast IP networks, we narrow down our collection to Anycast prefixes only. Hence, we filter out all the RIB entries that do not include a prefix in the previous dictionary that we mentioned in the first step. Now, let's go to one of my favorite, the most interesting steps of this methodology. It's the inference of the selective announcements. And to give you an example of what a selective announcement is, consider the following graph. In this graph, Meta is a multi-homed customer to both Lumen and Cogent. And based on our mental model of how the internet works, the Gower-Exford model, a network will prefer customer routes over peer or provider routes because customer traffic generates revenue and provider traffic incurs a cost. Hence, we would expect Lumen to follow a customer route to reach a customer prefix because customer traffic generates revenue. Nonetheless, Meta, who owns two Anycast prefixes, P1 and P2, decide to propagate an announcement to both providers for prefix P2, but decides to load balance its traffic and costs for prefix P1 by propagating an announcement only to Cogent, to their provider Cogent, which later on is going to propagate that announcement to their peer Lumen. Hence, when an end user behind Lumen wants to access prefix P1, they are going to follow a peer route, the one through Cogent, rather than the less expensive route or the route that generates revenue for the company through Meta, since they have not received an announcement by Meta to directly access that prefix. So, in a sentence, the definition of the selective announcements is that when an AS receives an announcement to an Anycast prefix through a more expensive route than what expected, then that prefix is called a selectively announced prefix. We measured the prevalence of selective announcements across Anycast ASs, and we observed that 84% of the Anycast networks announce at least one Anycast prefix selectively. And in this CDF here, what we plot is the cumulative distribution of the selective announcements per selective announcers. And what we observe is that this red circle over there tells us that approximately 80% of the selective announcers advertise all of their Anycast prefixes selectively. Hence, selective announcements is a common practice across Anycast networks. Now, the main goal of this paper, though, is to group the receivers of these selective announcements per the geographical region of the end users in an effort to try and capture regional trends that might arise so that we can later go and embody them in our simulations and refine the accuracy. And we rely on the intuition that when Anycast routing is deployed, the nearest POP site to the end user is going to attract the traffic. Therefore, when the client routes to an Anycast prefix, probably this route is going to be approximate to the origin AS in terms of geographic distance. For example, they might reside in the same geographic region. And as illustrated in this figure, the Anycast AS in the bottom connects to different sets of ASs in different POPs and selectively announces its prefixes to 4 out of its 6 direct neighbors. A bit of information that you need to know here is that large POPs are typically connected to both regional and global providers, while smaller POPs are mostly and usually connected to regional ASs. As a result, a client in region A, which is a region of a POP with mostly regional ASs, is more inclined to reach the Anycast prefix through regional providers rather than global providers. And this information, if encoded and incorporated properly in the simulations, can allow us to infer more accurately the providers that would transit the traffic from a specific to a specific prefix. So, to achieve that, first of all, to identify the regions of the end users, and then to label autonomous systems as regional networks or global networks, we need to geolocate ASs. And at least in this work, when we geolocate an AS, we consider 2 dimensions: the prefixes that an autonomous system announces and its public peering locations. And towards that goal, we extract country-level information for all prefixes announced by a network through MaxMind, through the RipeStat API, as well as extract the countries of its public peering locations through PeeringDB, through the PeeringDB API. Now, these datasets over here give us a glimpse of the geographic footprint of an AS. For example, to the left, you can see that AS 181.06 announces more than 90% of its IPv4 prefixes in Singapore, more than 90% of its IPv6 prefixes in Singapore and Hong Kong. And to the right, we can see that the same AS publicly peers with more than 50% of its neighbors in Singapore. In order, though, to reduce that country-level geographic footprint of each AS to the region-level granularity and be able to label ASs as regionals or globals, in this step, we leverage the United Nations regions dataset, which is a dataset that maps countries to the respective regions and continents. And for example, an autonomous system might geolocate in multiple countries, such as Portugal, Malta, and Greece, in the country level granularity, but the same AES will geolocate to Southern Europe only in the region level granularity. Hence, in our analysis, we can label it as regional. And we leverage this country to region mapping along with the previous AES geolocation dataset to label an AES regional or global if more than 90% of its prefixes and more than 90% of its peering locations reside under the same region. Now, to bring it all together, the last step of our methodology is to actually group the receivers of selective announcements per the end user region. And to do so, we extract all the direct neighbors of anycast AESs per anycast prefix. Those direct neighbors are the penultimate AESs in the AES paths that we collected in step 2. Then we group the receivers of the selective announcements that we inferred in step 3 per the end user region, using the country to region mapping that we compiled in step 4. And the result looks like the snapshot in the right, where AES 101.22 announces an anycast prefix to multiple regions like Northern America and Western Europe. Nonetheless, the receivers, the list of receivers that we can see here differ from region to region, allowing us to capture regional trends and disparities. Now, we leverage this dataset to measure the regionality of the receivers of selective announcements. And as regionality, we define the number of regional neighbors that receive a selective announcement over the total number of neighbors that receive that announcement. So in the x-axis, you observe the regions of the clients, the end users, per which we grouped the receivers. And in the y-axis, you can see the regionality degree of those receivers. So in these figures, we observe that selecting a regional upstream provider or peer to carry the traffic to a specific prefix is a common practice across these anycast AESs. Specifically in the use case of Cloudflare to the right, traffic is routed to the anycast prefixes through regional AESs when the source locates in the Sub-Saharan Africa, the Southern Asia, and the Western Europe in more than 45% of the times. And when it comes to Southern Asia, more than 80% of the receivers are regional networks. And furthermore, Amazon and Google exhibit more than 40%, their neighbors basically, exhibit more than 40% of regionality levels when the source AES locates in the Sub-Saharan Africa, the Southern Asia, and Western Europe, which indicates that in these regions and for these networks, there are specific regional trends that are followed. On the other hand, though, AESs like Fastly, BytePlus, and ZenLayer rely mainly on global AESs to carry the traffic to the rest of the internet, since the regionality levels are low across all end users' regions. Now, as part of our current and future research work, we aim to reason about the factors that drive the need for selective routing towards regional neighbors. Some of these factors, from what we believe, might be the deficiency of the lack of a centralized backbone by the anycast AES, lower transit fees that regional providers offer against public global providers, and strict regulatory conditions. Yes.
If you can wrap up fast, otherwise we will run out of time to make some questions.
10 seconds. And strict regulatory conditions that might apply in specific countries. So to wrap it all up, user-to-site mapping relies heavily both on the geolocation factor and the routing policies across AESs. Large part of anycast AESs deploy selective announcements for all of the anycast prefixes, and anycast networks often resort to leveraging regional providers to establish connection between their POPs and the end users. As a final remark, from our experiments, it is evident that network operators take different decisions in different areas. So when we simulate routing scenarios, if we do not take geolocation into consideration, that might have implications to the accuracy and the fidelity of our results. Thank you for your time to watch my presentation, and I would be happy to take any questions.
Thank you very much, Sabas. Do we have any questions from the floor? Maybe one question from my side while others think about it. So you geolocate the prefixes, right?
We geolocate the prefixes at least for the first dimension. We geolocate the prefixes. Yes, that's what Max might do.
My question was a little bit of nitpicking. So do you geolocate every single IP in a prefix? And if they are not all in the same location. How do you go around that?
It's not a problem that we deal ourselves. It's a problem that Ripestat API actually does. So that would take an enormous amount of machines that we don't have in our hands to do it. But if you go to the Ripestat API and find the MaxMind tool, you can see that they geolocate an AS per the prefixes that they announce. So we took it as a black box, if that answers the question.
Yeah, thank you very much. And we have a question from Matthias Wallisch.
So a brief question regarding, so you found different groups of, let's say, CDNs that behave differently. I mean, can you go back to the slide? I think it was
Yes.
right before the conclusion, where, yeah, exactly. These three compared to the other three. And did you find any other indicators that might give a reason why they behave the way that you found? So
we could have a large discussion on that. There are many reasons. For example, there are some. We spoke with some network operators in RIPE a few months ago, and they said that in specific regions they don't care about latency; they only care about jitter. So it depends on the business model of each autonomous system. But if that was not just a short paper but a full paper, one of the things that we would try to do is group these regional trends per the AS type, so that we can tell, for example, how an ISP behaves, how CDN behaves, how other types of networks behave, but we didn't, at least in this work.
it would be interesting to relate this to additional features, let's put it that way. Yeah. Okay, thank you very much.
Yes, thank you for your suggestion.
Right, very well. Unless there are any other questions, let's thank the speaker. Thank you, Sabas.
Thank you very much.
And is the next speaker in the room? Yes. The clicker, just 1 second. Yes. Okay, here we are. So we have now Bernhard again. Apologies again for mispronouncing the name, but it's not the only thing I mispronounce. So who is going to present an empirical characterization of Anycast convergence time. So continuing with Anycast, the floor is yours.
Yes. Thank you. I will be talking about Anycast, but from a different perspective this time, namely from the convergence perspective. This is a study I did together with Matthijs Jonker, Roland van Rijswijk-Dij, Rafael Semese, and we're all at the University of Twente. So what do we mean when we say convergence? As a quick reminder, convergence is the time between a BGP update and when the global routing system reaches a stable state. We know that BGP's convergence is impacted by factors such as the minimum route advertisement interval and route flap dampening. But it's not clear how much exactly. And in particular, we want to answer the question, how long should we wait after an announcement, but before its effect can be observed? And we're particularly interested in this in an Anycast scenario. Should we wait? Now I am waiting. It seems to be stuck. Okay, there it is. Should we wait for 2 minutes, 10 minutes, 50 minutes? We have seen all these values in literature without much substantiation. And this is particularly interesting for research, but also for operations. For research, we would like to know how long we should wait before we measure, so that we ensure that we measure the right thing. And for operations, it's very relevant so that we can swiftly distribute traffic over vantage points, over points of presence. So the goal of the study is to put BGP convergence time on an empirical footing in an anycast setting. Now I will go over the methodology that we use in this study. We run our experiments on an anycast testbed that we maintain ourselves. And we measure, we do a set of announcements and we measure the changes it brings about. So as a first step, we have a hit list. We use a /24 hit list, which contains the most likely address to respond per /24 network, which is the maximum routable prefix length in the default-free zone. And we pre-process this hit list by rejecting addresses that are not responsive. And we partition this for to quickly perform our scans for optimizing the turnaround time, because it doesn't give any extra information if we scan each address in a /24 hit list, or if we just select one representative address for that /24 prefix. Now, for each partition, we announce a prefix from a set of vantage points. We start a catchment mapping procedure every 10 seconds for 5 minutes. So one catchment mapping takes about 10 seconds. A catchment is basically the set of IP addresses that is routed to one anycast POP. And we repeat this for 4 sets of VPs, or we do this in total for 4 sets of VPs, 6, 12, 18, and 31, to represent anycast deployments of varying sizes. We use 2 catchment mapping methods to ensure that we use the right approach. So we do forward probing or forward measurements, which is basically the wide scale probing that I just explained. And we do also something we call reverse probing. And that is not sending the probes from our testbed, but rather using CADA's distributed arc measurement infrastructure to probe our vantage points. I will explain these 2 methods in the next slides. So what do we mean by forward probing? This is basically what is referred to in literature as Verfluter style measurements, where we have a server and a bunch of vantage points. In this example, we have 3. Vantage point 1 and 2 have an active announcement, and vantage point 3 doesn't. So the server delegates a part of the hit list to a vantage point, which sends out the probes. For this study, it doesn't matter which vantage point that is, because we are interested in where the replies are routed to, and not so much where the query is coming from. So the client at vantage point 1 sends an ICMP echo request to the target on the hit list. And that target then replies, in this case, to vantage point 2, but it could have also replied to vantage point 1. Vantage point 2 then sends the result back to the server. Now, what is the result of this? We get actually a fine-grained measurement of the catchments at the /24 level. In parallel to the forward probing, we do reverse probing. And we use CADA arc nodes for this, which query our vantage points via DNS. We use DNS A queries, and each name server running on the vantage point has a unique identifier for the same query. So based on the reply, the DNS reply, we know which vantage point is replying. The downside of this approach is that it has less granularity. It's only 149 ARC nodes at the time of measurements, as compared to 3.92 million active hit list targets we use in forward probing. Then I will go over some results. So the first result is a graphical depiction of how the catchments are distributed. On the y-axis, we see the catchment distribution, which is normalized to a value of 1. We can do this because there is very little variance in terms of number of total responses per scan. And on the x-axis, we see the scan index. So we start off by 6 announcements, and we see the resulting catchments. Then we do 6 more, and 6 more, and the final batch of 13. Now, a couple of things become apparent from this plot. First, we see that catchments vary vastly in size, And even though we announced 6 at the beginning, 6 vantage points, we only observed 5 of them. The 6th one is actually there, but it is so small, it is too small to see in this picture. Next, we see that some vantage points take preference over others. So after we announced the second batch of vantage points, suddenly the blue catchment in the first region completely disappears because clients shift to other vantage points which take preference. Now, the main result of the study is, of course, the convergence times. That's what I promised. And on this slide, you see on your left a table which lists the convergence times at the 50th, 80th, and 95th percentile, along with standard deviation. And on the right, you see the same thing, but in a CDF. We define convergence here as the moment at which a prefix no longer changes between catchments. So when the routing of one prefix remains stable. What we can see in this graph is that 80% of the population that we measure already converges within the duration of one scan, which is about 10 seconds. What we also, what you can also see is in the CDF, there is a straight line between the 0 and the 10 seconds, which corroborates this result because the probes are sent out linearly and at the uniform intervals. We also see a noticeable decrease when we announce more vantage points, particularly when we go from 12 to 18. We surmise that this is because catchments become smaller as there are more active vantage points, so less routers are impacted by the announcement. Then for the reverse probing results, we were surprised to see this graph where it appears that most clients seems to be converging near the end of the measurement period, particularly when 31 vantage points are active. So this warranted more investigation. What is going on here? It turned out that 11 of these nodes are not converging at all and were flapping between 2 or more vantage points. We thought about this result, and the most likely explanation that we found is that these are DNS queries being sent by KDA's ARC, and KDA's ARC API does not allow tight control over the exact packets that are being sent out. So every packet has a unique source address, which make our measurements subject to load balancing. After excluding these nodes that are not converging, we end up with a graph that looks more similar to our forward measurements. Still, the difference of 31 vantage points is there. However, we only have 12 in total that change catchments in this measurement round, so we don't have enough information. In conclusion, we devised a method for measuring anycast convergence, which measures it from an end host perspective. It doesn't require cooperation of end users, and it measures the global routing system. We find that 80% converges within 10 seconds, which is the duration of our scan. And we find that convergence happens faster when there are more active announcements. We have some further ideas. Namely, first of all, we would like to increase the measurement resolution. If we scan faster, we can obtain more precise results. And we would also like to zoom in on regional differences. Right now, we use our entire testbed of 31 VPs. However, most of the VPs are located in the global north, which doesn't make the measurements representable of the internet as a whole. And finally, we would also like to look into how IPv6 behaves in this regard. Thank Thanks for your attention. The paper is online at this link, along with the complete measurement data sets. I'm happy to take questions now, or you can always send me an email.
Thank you very much, Bernhard. Do we have questions from the floor? Yes, I see Matthias with a question.
Hello. Actually, I have a couple of questions, but so first, when you talk about testbed, you are still running your experiments on top of the internet, right?
That is right.
So you mean that you have the vantage point under control and injecting, okay. Other question regarding the hit list and second slide and the 24 prefixes. I didn't get the point with the splitting. Can you go back? Even more. Okay, shuffle and partition, the partitioning. Okay. So does it mean that you split up the 24 even more specific prefixes? No, right?
No, not more specific prefixes. Yeah. But we take the entire hit list and we randomize it and split it into 40 partitions. And we do this so we can quickly perform one scan without losing generality. So we still target every /24 prefix on our hit list, but we have a quick turnaround time of one scan in 10 seconds.
So, and the hit list includes multiple /24 prefixes?
Yes, that's correct.
Okay, great. And obvious question, did you compare the conversion times with non-anycast prefixes?
We have not done that yet. Okay. We did look at convergence times in literature, okay. But we have not measured this.
Okay, good, thanks.
Thank you, Matthias. Next in the queue is Robert.
Robert Story, USC ISI. Did you run the ARC, the reverse measurements, at the same time as the forward measurements or different?
Yes, we run them at the same time to ensure that we're measuring the same thing.
And maybe one quick question from my side. Did you compare with root collectors to see if the active measurements that you are aligned with what you see there?
We have not done this. We did consider this, but our focus was more on the end user perspective. So how routing propagates within a network.
Oh, very well. Thank you very much. Let's thank the speaker. And if the next speaker can approach to the table, I'd really appreciate it if people could scan the QR code and be available in the data tracker. In particular, if you are a speaker, so it can actually ping you and tell you in advance to come and get ready. So you will use this, and the slide deck will be there in a second. At the moment now, it's the version that is uploaded there. So
yeah, sure. But that's... Okay, can you? Okay, because last night I inserted the new version and it was accepted.
So then that's this one. Yeah.
So moving this.
Yes.
Is the laser point?
Yes. Yes. So we have now there making diffusing computations more efficient on for loop-free shortest path routing with Morteza. I won't attempt to pronounce your surname. Apologies for that.
No problem. So good afternoon, everyone. It's really a pleasure being here with you today. Today I'm presenting, by the way, my name is Morteza and I am a research associate at University of Toronto, where not long time ago, I also obtained my PhD and completed my postdoc in the same place. So today I'm presenting DARE, which is a new routing protocol focusing on hopefully making diffusing computation more efficient. And this work is co-authored by Professor J.J. Garcia, whose novel brain and ideas have led us to the invention of DARE. So basically, throughout this presentation, I will focus on discussing three important things with regards to DARE. These three topics is first the motivation that speaks to why do we need another yet diffusing computation where we have dual and it apparently works in the IGRP right now. And then I will cover a discussion about DARE and when we say efficiency, what do we mean? Making it faster to converge and less overhead in terms of signaling. And the third one is we compare there and dual in terms of the routing methods, and hopefully to get you there to understand where we are putting our eyes on the improvements. So it's good to begin with a bit of context that why do we really need a diffusing computation in the first place, is that if I drag you back a bit to distributed Bell-Manford, well, the algorithm is really working and it's efficient, especially if you consider the minimum hop routing into your routing, and it works in many scenarios. But the main problem that we have with Bell-Manford is the count to infinity. And the count to infinity problem, regardless of how we engineer the network to get rid of that, but the problem with the algorithm exists, and that led us to the emergence of short or sometimes even long-lived temporary loops in the network, which then it means for us that we're losing packets or sending packets to a network where there is no actual destination for, let's say, a temporary amount of time. That's a waste of resources. And in an example that I continue to be persistent with dual and there over this set of nodes that you see here, is that if I have this five node network, if the link between A and D fails, then obviously the node A in Bell-Manford start digging around its neighbors to find the shortest path. And that would cause the node A to select the path to go to C because C advertises 4, and then adding the link weight 1, it becomes 5. So apparently 5 is better than this path that is going 7 through E. So then node A picks that and then start advertising to its neighbors, which then causes node C, who was before going through node A, to pick that and increase its own weight and start updating others. And in a sequence of updating each other, that flow continues to be there until something happens like the value of the count to infinity increases beyond the value 7 that can be advertised by node E to go through D, and then we stop there. So sometimes this is just a few steps, sometimes this is like a much longer step, and we stay in loop, and unfortunately this is happening every day. So by that, we can see that not even far into the algorithm, in the first few steps, we see the temporary loops to emerge. And I would say that's a bit of wasting of the resources. However, the algorithm works overall. I'm not debating that. So now this is a form of distributed computation, of course. But if we go to dual is also doing a distributed computation for us. However, the language of a dual is a different form of doing distributed computation called diffusing computation. So basically, there is a system of query reply between the nodes to synchronize over the failures or changes or updates in the network. So each node, each router that you have in a dual network considers itself either passive or active. That's simple. If you are passive, that means you're good, and whatever is your next node to a destination, that can stay. But if you don't know because of a change that what would be the next node, then you have to choose the next one. And if certain conditions, which we call this a local condition, cannot be satisfied, then you have to ask your neighbors. So a local condition would be, let's say, if we consider the hop count here too, a local condition would be if any of my neighbors can give me a better distance in terms of the hop count than my feasible distance, and by feasible distance I mean my current path to a destination, and that is also the shortest path, then I'm happy. But if I'm not getting that from my neighbors, then I don't know where to go. So then I go into an active mode and set my feasible distance to infinity because I no longer know where to go. And that then causes me to also stating new distances to my neighbors, which we refer to that as now diffusing. So then the problem is I have to wait and wait and wait until all my neighbors reply to me and telling me where to go to make a decision. And if that becomes a domino effect that I talk to many people and then to many neighbors and then many neighbors talk to many neighbors, then all of us have to wait on each other to make a decision. And that would be also a problem. So let's say everything goes well, hopefully, and then the computation of new distance happens. Then my local condition becomes satisfied, and then I go to a passive mode. So with that in mind, let's take a look at the same network that we were doing with DBF, now with dual. The same link breaks, of course. So the moment that that happens, node A set its feasible distance. You see two weights on top. One is the feasible, the other one is your current distance. So you set your feasible distance to infinity, and you don't know where to go, but then you can send updates to your neighbors, and then you have to wait all of the replies to you to come back to make a decision where to go. But unfortunately, in a step C, you can see that that can cause the next node to go to a diffusing computation or active mode, because the update you sent to that node, the node was set to go through you. So that means the node doesn't know where to go. So, and that's a domino effect here that you can see. The unfortunate situation is you're already getting a reply from node 2 that you can go by a node E to D by 2, which means you can go by 7. And that's a valid advertisement, but you cannot pick that in dual because you're stuck with all of the replies to you first to come and then make a decision. So short story, that goes into a sequence of query and replies until you hear from all your neighbors and you then converge yourself first, which then that means you can now choose to go from A to D, and then you can update all your neighbors and then they can converge. Well, of course, you see more steps here, but then no router has actually put you into a loop. So packets in the network at least don't wander around, and you're not misusing the networking resources just because of the routing and signaling that you need. However, we believe that this algorithm, even though it's perfectly working and it's efficient in its what it is intended to do, may have its own issues. So the key issues here is what I just referred, is that you're set to only do a single loop free next hop. How about multiple of them being available to you and you cannot choose them? But if you could do, then you could reduce your signaling significantly. And the second one is, well, I have to go into sending a query and then making a diffusing computation, but then I have to wait until I can choose my next hop. And that would be some of my neighbors can actually offer loop-free routes that are valid to me, but I cannot choose. I have to wait, and that waiting time is unknown. Depending on the domino effect that you put on the network, you may hear from them at different times. Okay, and then so this unnecessary blocking, we believe that it also slows down the flow of the data in the data plane, because it does, right? When you block and you wait until to make a decision, so that the flow of information is uncertain in the network. So considering these challenges had led us to there. And of course, if I want to say the first thing that you need to know about there is, well, there is compatible. It's not that we're making a whole change in the way that the language of the protocol is or the way it is working. So hopefully it can stay within the same infrastructure that we have today or used in the same context. However, with there, we changed the definition of what a feasible next hop is. And that's very important because in dual, all you make a decision is who's the next node that can lead me to a destination, right? So the language tells us that a feasible successor in dual, a feasible successor means your next hop to a destination, okay? Is any neighbor that can give you a smaller distance that you believe right now, but it has to also be the shortest path. Emphasizing so much on being the shortest path make a type of restriction and limitation that may actually not be necessary at the time of the competition, but you can lead on to afterwards. So in there, the feasible successor is any of your neighbors that can report the distance to you smaller than the distance that you had when you were passive. So before you become active, you had a distance that can be considered as that. And that small change allows your neighbors to report to you shorter distances that you update them with your stating new distance. We will see an example of that coming up and how that actually roll the network with that new updates. Then basically we call any of those neighbors that can give you a shorter distance than your current understanding of the distance or your feasible. We call them ordered routers. So you only need to go to a diffusing computation if you don't have any of those ordered routers, or none of the ordered routers that you have can give you a strictly shortest path. Okay, maybe the passes are equal, which you don't consider them as ordered anymore. So with that, I'm just trying to say that that implies that also in there we decouple the calculation we need to do the shortest path calculation from the selection of the successor node. You can temporarily select the successor node just to avoid misusing the networking resources, but then the calculation converges to a shortest path later. Okay, so the second note about there is there remembers what dual forgets, and that's very important because in dual, what happens is dual routers don't remember which of their neighbors put them into this diffusing competition, and because of that, what happens is they need to reply to every neighbor after they figure out what they need to do, and then that is an excess overhead in the network. Plus that they can only now participate in a single diffusing competition, because if I don't remember and I'm going to talk about my beliefs to everyone, then I don't remember which one was that, so I can run only one diffusing competition. So, but then in there remembers exactly which node forced the router to go into a diffusing competition. So it only replies to that particular node, which means much less signaling in the network. Plus that I can run multiple diffusing computation in there, and even I can combine them for different decisions if I am in the active mode. So then I can be faster in my convergence. The third to know about there is fair, not that I'm referring to the fairness concept in networking, but also to the position that dual routers can only change their successors when they are basically satisfied with their local condition, or everything about the diffusing computation is completed and they go from active to passive again, so they can make a change. But as I said, and I just showed you in an example, that would be a domino effect and takes so long. But in there, you can change your successor at any time, regardless of whether you are active or passive. Just make a change if you need to. But the thing is, you only need one of the routers to tell you a shorter distance than when you were passive, which happens quite a bit in the networking, that you get that neighbor that tell you this, and we are going into an example to show that. The other thing about that we think there is fair is dual state machine is so complicated. Because of all of the challenges that I said, the state machine is complicated. So that makes the evolution of the protocol a bit challenging and also hard to imagine if you want to adapt new criteria for your performance in the network. However, with their state machine, we can be hopeful that because it's much simpler, we can evolve it faster and adapt new performance criteria. So I talked a bit about the state machine. Let's see the state machine in there. It's pretty simple. We still have the same language that we speak as dual, passive and active mode for a router. And when I say passive and active, I'm trying to refer to the fact that a router either needs to make a decision on its own knowledge, which means you are in a passive mode and you believe you know what you need to know, or you don't know and you become active talking to your neighbors to find out. So you can be in passive mode with there up until the time that any link change or update still keep you satisfied with your local condition, or any query that you receive from your neighbors does not change your belief. An example in the same five nodes network is that if the link between B and A changes weight from 30 to 20, what you can see is that doesn't change the belief of node B, because B is set to go via C to destination D, and that link is 3. So 30 or 20 doesn't make any change. So you're still in the passive mode, and you can see 3 values on top of the there here. One is your current distance, and then your feasible distance, and the one that you also report to your neighbors. Okay? But then you go in from passive to active if the local condition doesn't satisfy anymore. What if I lose this link? Well, if I lose this link, the weight is 3. So then I don't have any access to this node, which is my destination. So node E now has to make a decision. However, the next node, which is the only neighbor here, advertises a weight 8, which is above the 3 that I have here. So I don't have that ordered neighbor anymore. So what I do is I can, at the same time, I can send a query to find out who's my next neighbor to that destination. But also I changed my successor and picked the path from E to D via A by weight 13. So I'm not stopped and I'm not locked. I can still forward your packets to that destination. Maybe the path is not your preferred, is not your shortest path, but it can still work until all of the diffusing computation completes, and then we get a complete path. So you can stay inactive if in active mode. If the input even still is there, and then you need to coordinate with the neighbor, let's say the neighbor B, you need a response from it, so you wait for the response before you become passive. And if the local condition is still false, and you may not coordinate, but still your local condition is false. But the moment that these are going away, you can easily go to passive mode by saying that my local condition is satisfied and I don't need to coordinate with anyone else. And that would be, in this scenario, that would be just a single reply back from node A to E telling you, hey, you can go through me by 5, and then you adapt and then become passive right away. So no bit of challenge in the network if that happens. So now let's take a look at the same scenario that we ran with DBF and then later with dual and now with DARE. Well, the event that happens in the network consistently the same. We lose the link between A and D, 3. But the moment that happens, then you pick the next neighbor that advertises to you a shorter distance than what you believe. Okay, so this is advertisement of 7 because the pass here is 5 and 2, 7. But hey, you lose the link, right? So after you lose the link, you believe that you no longer can reach to the destination. So 7 is actually pretty viable for you to pick. So while you are in diffusing competition, and you can see I changed the color to indicate that I am in active mode, I choose to go from this pass until I hear from all my neighbors regarding the query that I sent to them, and then make a decision that whether my decision at the beginning was okay or I can go now. And that would tell me that I can send updates with weights of 7 where my neighbors can report back to me with shorter distances. But I already picked one, so I wait until this query reply goes on and then make my final decision. But I did not, as a result of that, I did not block the network, and I never sent excess overhead into the network because of that. So hopefully the loop-free routing stays there with a better performance. So to make a few final remarks, is that DARE by itself is a new routing algorithm, only improving the existing work, but it is by nature a new algorithm, and DARE speaks the same language as Dual does, but it does that so that it can make your state machine much simpler and less signaling and faster convergence, and gives you the flexibility to choose any available neighbor. So the capacity of the network is always available to you as a routing protocol to choose, regardless of what state you have. And finally, we hope that the next step for us is that we can incorporate DARE into a routing protocol to see the result at larger scales. So many thanks for your patience, and I'll be happy to take any questions.
Thank you very much. Questions from the floor? I see Juan Camilo has entered the queue. Juan, please go ahead.
Can you hear me?
Yes.
Hello, thank you for your presentation. So in the practical side, it wasn't clear to me. Could like a network in which half the devices are using DARE be compatible with other half of the network using dual, for instance, or everything has to be converted to DARE for this to work?
Well, okay, the moment that I discussed, I guess you're referring to this chart. Well, when I said DARE is compatible, it means that the DARE language of going from passive to active and active to passive stays the same as dual. And the transition from passive to active only changes because of a configuration because of a change in the meaning of a feasible next hop, which is hopefully a software or let's say an implementation change that we can apply, but no need to change the infrastructure that runs the algorithm. That was the main point, I guess.
Right, but again, if will DARE device interoperate with a dual device or not really? It's okay if it's no. I'm just wondering.
I think we lost you, Juan.
I'm just asking whether a DARE device will interoperate with a dual device. That's all.
No, in terms of in terms of interoperability, I guess DARE and dual cannot speak to each other, if that's what it meant from the interoperability perspective. But
it is. Thank you. That's okay.
Yeah, sure. Okay, yeah.
Thank you. And I see someone in the queue. Well, I see someone on the microphone, not on the queue.
Sorry, it's Tony Lee, Juniper. On-site devices being weird. Anyhow, have you done any simulations to compare against link state protocols?
Sure. Well, our simulation is undergoing. in NS3. However, we have done some early assessments. The figure that you see here showing a particular topology that is intentionally making domino effect. If this link goes down and A go to D, if it was dual, all of these nodes went to diffuse and computation, and then all of them should come back. While this alternate pass WAB is available. So in dual, that would cause sending 30 messages for a 10 node network. If by 10 node, I mean 1, 2, and 3, and then the rest 7. That would send 10 messages, 30 messages for a 10 node network, and also 14 blocking steps. By that, I mean A to V2 is blocked and V2 to A is blocked because it's bidirectional, right? However, if it was there, 0 blocking happened as a result of that, and then the number of messages is much smaller. Now, if you scale to go to a 50 node network, you would see that 94 steps blocking can happen as a result of a link failure, but in there is 0. But that's one of the earliest results that we have, but we are continuing to do so.
Okay.
Yeah.
Comparison against ISIS would be interesting.
Of course, yeah.
Thank you.
We'll have. Thank you very much.
Well, thank you very much,
Thank you.
Morteza. Thank you very much, everybody. Let's thank the speaker. And right here is our next speaker. So now we have, okay, this is going to be hard. I'm just going to say your surname. Nadas. Is going to present to QoE or not to QoE, towards QoE, our resource allocation for real-time media. The room is yours.
Sam Sylvester from Ericsson, Santa Clara. So when we talk about real-time media, we focus on mobile video use cases. We group mobile video into 3 different categories: real-time, near real-time, and non-real-time. And real-time is when some kind of interactivity is included, either a human or AI or an organism in the loop. And therefore, like, a very small latency is required to keep that interactivity active. We say it's 30 to 110 millisecond fingered photon latency. And applications for that include remote rendered XR, cloud gaming, and remote control of different drones, cars, and heavy equipment. Video conferencing, like the one we have at the moment, are to some extent interactive, but the interactivity is much lighter. So we say it's 100 to even 500 millisecond RTT is acceptable. And then when we watch video over the internet, whether it's being live, like a sports event, or just video on demand, much higher delays are acceptable, like 1 second for live content, and much higher, like 10 to 90 seconds for video on demand. So what characterizes the QE of real-time video? We say there are 3 different components of QE: spatial quality, temporal quality, and input lag quality. So temporal quality requires high and consistent frame rate and no visible freezing, for example, due to frame drops. And input lag quality requires the already mentioned fingered photon latency to be small. So it's, for example, a button press until the resulting action is somehow visible. And because for real-time video, these 2 have to be kept low, the frames must be transmitted in a few frame times. So each and every frame is probably transmitted in a different series of packets, and there is no long time averaging like for that. So we cannot create chunks of contents of 2 to 10, maybe even 30 seconds long, and aggregate these frames and have basically TCP downloads. It has to be some kind of real-time protocol. And because of that, the spatial quality becomes important in a way. So what is spatial quality? Spatial quality is the visual picture quality versus the perfect picture. It's not simply the resolution, it's the effect of the bit rate. Depends on the bit rate, on encoder configuration, also in the content itself. And there are different metrics for that. For example, Netflix is VMAF metric, or ITU P1204.3 and other metrics. And that's the focus for our talk. And again, it becomes more important, more bursty, because each and every frame has to be transmitted separately. So how do we characterize spatial QE? It is something we call the spatial complexity curve. And that measures spatial QE, for example, VMAF score, as a function of average rate. So what we did to determine this curve is that we took 10-second long homogeneous HD video game clips and encoded them with different target rate settings. We calculated the VMAF spatial QE measure for each and every encode. That is spatial quality measured by Netflix. That was developed for movies. It's open source, and it is to some extent applicable for all kinds of contents. And we say that 50 is a minimum acceptable quality, 70 is already good quality, and 90 is close to perfect quality. We took a bunch of games, 12 games in total, from racing, third-person, isometric, first-person shooter, platformer, card, real-time strategy, and sports. And we actually order them in the order of complexity decreasing. So Racing 1 is our most demanding game. It requires more than 11 megabits per second to reach VMAF 70. While the sports game, which is basically like most, in this case, a field from above and not changing very much, requires less than 1 megabit per second. But again, I want to emphasize that these are homogeneous clips on purpose. The games might be more changing than what is visible here. This is like one state of the given game instead of characterizing the whole game. So what can we do in our network if we want to take advantage of this heterogeneity? So how does cloud rendered gaming looks like? We have cloud rendering servers where the game is being executed. The frames are rendered by the server. They are encoded into video frames, sent over the transport, sent over the network, decoded into the cloud gaming clients, and the cloud gaming in the client, the user actually plays the game, takes game actions are being sent back to the cloud rendering server. So if we can have a QE controller somewhere in the network, how can that allocate resources more effectively than in the bitrate domain? It can get some kind of QE metrics from the cloud rendering servers. It can get also some metrics from the network. I will mention about details of that later. And based on this, so for example, the QE metric can be the spatial complexity curves on the previous slide. So based on these, it can calculate an optimal allocation from QE perspective and apply that optimal allocation by sending rate control messages to the encoders and maybe also control messages to the network. So, but this is pretty complex. So what is our gain? What motivates thinking about this additional complexity? So we calculated example gains of QE awareness, still the same data, and we said that our VMAF target is 70, which is good QE. And we determined the maximum number of flows for two different strategies. The first strategy is called equal bitrate. All flows get the most demanding games rate requirement. And that is because we don't have any information about the game. We don't assume any kind of cooperation between the network and the game. So if you want to make sure that a good QE target is met for all of the games, we have to take the most demanding games requirement. While the other strategy, the equal QE strategy, assumes that we have this architecture implemented and we are targeting equal QE for all of the games. And then all flows get just enough rate to reach VMAF 70. So what are our gains? Like if we take the two most extreme games, racing and sports, and just have games from these two, then we can only support 13 games with the equal rate strategy and twice as many games with the QE, equal QE strategy. Part of that gain is from granularity. We simply couldn't put like one more racing game into the system, and the sports game requirement is so small that it actually fitted into the empty space. What happens if we take less extreme game pairs like the green one or the purple one? Then, of course, our gain decreases, like from 2 to 1.72 or 1.33. There's still some gain. But if we have a mix of games, like all 12 games, then because some of the games have very high rate requirement compared to the others, the games can be extreme. So if you consider all 12 games with equal probability coming to the system, then the gain factor is 3.62, which means that we can have 3.62 times as many games as with the equal bitrate strategy. And even if we exclude the two most extreme games, the two least demanding and the two most demanding ones, and just take the sorry, the 8 games case, it's still twice as many flows which can be admitted to the system. So these are the good news. What are the complications? First, we have cellular network characteristics. A base station have a given amount of radio resources, and in an abstraction level, spectral efficiency determines the bitrate achievable with these amount of resources. And spectral efficiency varies as the radio channel quality varies due to mobility, noise, and interference. And in the analysis in the previous slide, we just assume constant spectral efficiency. There is more on dynamic spectral efficiency in the paper, but of course, if the spectral efficiency changes, the allocation has to be updated, and it's not that simple anymore. Also, an important factor where we actually received reviews and it wasn't like highlighted enough in the paper is that resource sharing over the air interface is determined by the air interface scheduler because packets are queued into per user or even per user queues or potentially even multiple queues per user. And these queues are scheduled, and any kind of desired end-to-end algorithm behavior when it comes to resource sharing is overridden by this queuing and scheduling. So the end-to-end algorithms cannot quite help unless we change how the base station is working, but there's a reason for that. The other issue is spatial complexity variation. For the 10-second long clips, which are designed to be homogeneous, we calculated the 1 second average rate required to reach the beam of 70 each second. So this is, again, the good QE, the same target as on this slide. But instead of calculating the rate requirements for the whole 10 seconds, we calculate it for each and every second. And you can see that, for example, for third person 2, the requirement varies between 12 and 6 megabits per second. So it's already this high variation for clips which were designed to be homogeneous. So if we implement a QE controller, it has to follow this variation somehow. Also, if we have non-homogeneous clips, higher variations are possible. These are our 2 extreme games, but different clips, the racing one and the sports. And so the sports is especially interesting because in the beginning, the sports game is having the same kind of behavior like 10 seconds. So it's a field from the top, not much changing. But then an event happens in the game and the game renders almost like a real life experience. And suddenly the requirement jumps up from about 1 megabit per second to 10 megabits per second. So it's 10-fold increase. So if we implement a QE controller, it has to be able to follow all these variations to some extent. So how we would design such a QE controller? The simplest algorithm, and that is what we have calculated the gains for also, is to provide equal QE for all flows. And that is when we have full knowledge about the spatial complexity curves and we send rate guidance to the encoder in the servers. And we always, when we calculate the amount of resources, we always give resources to the flow with the smallest QE. And among equals, for example, the one with the highest spectral efficiency, potentially also have a minimum QE requirement and reject flows for which this minimum QE requirement cannot be met. But again, this calculates the amount of resources to each flow to reach the equal QE and send rates guidance. And if we want to handle spatial complexity variation and apply the single algorithm, we have to recalculate the QE controller allocation with some frequency, like every second, every 2 seconds, and so on. Similarly for spatial complexity variation, the same thing. But there can be improvements to this algorithm. And kind of my favorite improvement is to use QE guidance as opposed to rate guidance. So if you have a look at the algorithm itself, it says it looks at QE metrics and send rates control. But what if we can send instead QE control, which means that we send, okay, target VMF 70. What will be the result of that? The QE itself will be much less bursty because we provide the QE guidance, but we need an encoder which can actually do that, which can actually do QE targeted encoding. And we trade burstiness in the QE domain to burstiness in the rate domain, which might still be okay. If we have several of these flows and they are statistically multiplexed, the resource demand of the whole set of real-time flows might still be reasonably stable. We can, if it's over a given amount of resources, we can still react on that by decreasing the QE target. The other potential improvement is to work with only having partial knowledge about spatial complexity. Calculating these spatial complexity curves all the time is obviously quite computing intensive. What if we only use the current QE level and the current bitrate and try to estimate what happens if we change the QE or the rate guidance? We can also take into account the resources needed to reach a given QE, for example, by using utility functions. The reason for this, If there is a flow which requires disproportionately high amount of resources, either because it requires high rate or because its spectral efficiency is low, then we might still want to give it reasonable QE, but we don't want to give it the same QE as others, because that would be like a very disproportionate decrease for the QE of the other flows. It is still QE aware, but it's not equal QE anymore. We calculated the equal QE because it's very easy to compare, very easy to calculate gains for, but that's not quite a realistic thing to do in a realistic system. And lastly, it can also implement service differentiation, like gold flows having higher QE than silver flows. And in conclusion, we demonstrated the high potential for scalability gains by moving traffic management from the bitrate domain to the QE domain for real-time media flows. But for that, an interface for application network collaboration is needed to achieve this gain. And there is a very serious trust issue, which is very far from being trivial to solve. There are benefits, and users have increased QE, carriers have lower contention, cost saving, less capacity is needed in the networks in general. Service providers can offer a more consistent QE, but high amount of cooperation among players needed. The trust issue has to be solved somehow. And we are active in this area, and we welcome discussions in this area. I know it's to some extent it relates to the SCOME Pro discussion we had in the other room this morning, but it's a much higher complexity, much more trust is required in this case. Thank you for your attention. I'm open to questions, comments.
Thank you very much. Do we have questions from the floor? Maybe one question from my side. Do you think that it might interact with net neutrality regulations?
Yeah, it depends on how you implement it, but of course, in general, when you move traffic management from the bitrate domain to the QE domain, you have to think about net neutrality. If there is a perfect trust among players and it's well coordinated, then it might be net neutral in the spirit of net neutrality. I don't know about the law of net neutrality, whether it's net neutral in that case, but that's part of the puzzle to solve here.
Yeah, fair enough. Any other questions? If there are no other questions, let's thank the speaker. Thank you very much. And could the next speaker approach? The slides will be up in a second. And then you can just control the clicker. Just hold on a second. I need to be up first. No. Yeah. Yeah. All right. So we have now Fatih Berkay presenting to switch or not to switch to TCP Prague. Incentives for adoption in a partial L4S deployment.
Hi, everyone. I am Fatih Berkay Sarpkaya from New York University, a PhD student. Today, I'd like to present our work about partial L4S deployment, actually. Let's start with what is L4S. Actually, L4S is an architecture for low latency, low loss, scalable throughput. And scalable congestion control is the key part of this L4S architecture. We can see this by looking at these plots. Actually, these are the plots that we generated with our experiments. And you see the congestion window over time plots here. And in the first plot, for instance, you can see that we use, as a classic TCP congestion control, we use TCP Reno. And in the first plot, we see that if there is no ECN support, as we already know, the classic TCP increases its congestion window size until it fills the buffer. And in this case, we can have very high utilization, but also we will have high latency actually because of the queuing. But in the second plot, if you look at here, if we use, let's say, 20 millisecond ECN threshold, in this case, the sender will increase its congestion window size until the ECN limit instead of the whole buffer size. So in this case, we will have lower latency because of this ECN limit. And we can have, again, maybe high utilization. But the problem starts when we want to get very low queuing delay. If you want to get very low queuing latency, we want to set the ECN threshold very low, for instance, 1 millisecond ECN threshold. If you want to do that with classic TCP congestion control like Reno here, as you can see here, it starts to increase its congestion window, but we have very low ECN limit. So it increases its congestion window until that 1 millisecond. But in this case, we can get maybe low latency, but we will have very high underutilization actually. We will see lower utilization because these classic TCPs require some queuing to increase their congestion window. So in this case, it won't be able to find enough time to increase its congestion window, so we will see some underutilization. In this case, scalable congestion control, such as Prague here, can solve this problem. In this case, as you can see here in the last plot, even with 1 millisecond ECN threshold, because of Prague's congestion window, we have very fine sawtooths, very small sawtooths to adjust its congestion window according to the congestion level on the network. Because of that, it can get high utilization even with very low ECN thresholds. So because of this, scalable congestion control is the key part of this L4S architecture. But it's not, this L4S architecture is not restricted to this scalable congestion control. We have some more elements. You can see here the whole network architecture. We have senders and hosts, servers and hosts, routers. And in this case, I already mentioned that we need scalable congestion control on the sender side at least. Let's say this is a server here. And also we need accurate ECN support to get this very small sawtooths for TCP Prague to get this very accurately change our congestion window. We need accurate ECN support on the end sides, and also on the routers in the middle boxes, we need ECN support, of course, and we need shallow ECN marking. We need to implement this to get low latency benefit, and also we need to, because of this different behavior of classic TCP and scalable TCP, we need to isolate them because it's obvious that we need different ECN thresholds for this different kind of TCPs. So we need to isolate them. So we need multiple queue or dual queuing system on the router. So as you can see, we have so many things to implement on the network. So it means that we cannot do this all at once. We need some incremental deployment to L4S. And here, as I said, we need incremental deployment, and you are seeing now some example scenario from RFC 9330 document. In this example scenario, they assume that first we have DC TCP on the sender side. It's again another scalable congestion control, but for the data centers actually. Then after we first implement the L4S AQMs, this is a dual PI2 actually. It isolates the L4S AQM, isolates the scalable congestion control and the classic ones. So we first implement this, then we upgrade our senders to have TCP Prague and accurate ECN. So it means that in this ideal scenario, let's say this is just an example from the document, but let's say this is an ideal scenario. In this case, L4S flow remain isolated from classic flows because we first implement the L4S AQM on the router. However, we can say that in other sequences, scalable flows can coexist with classic flows at L4S or non-L4S bottleneck routers. So there are likely to be scenarios such as L4S flows will traverse non-L4S AQMs, such as peering points, non-cable access links, 4G, 5G, Wi-Fi, satellite. This could also happen. And also another challenge is upgrading legacy access network middle boxes, such as Wi-Fi routers or 3G, 4G base stations. Support L4S will be a challenge, actually. You need to upgrade these middle boxes to support L4S, so it will be also a challenge, actually. These are the points that we want to list. And during this incremental deployment, there are some, to encourage this incremental deployment, actually, we have some items we listed. First one is an L4S flow should have throughput and delay characteristics at least as favorable as a classic flow, even if some elements of the full architectures are missing, to encourage us to implement L4S widely, actually. And also, of course, an L4S flow shouldn't be harmful to classic flows during this incremental deployment, to encourage us to implement L4S, actually. In the literature, actually, if you also look at the IETF meeting notes, we have some also early tests already. And these tests raise some concerns. I just wanted to put some of them here. You can find more. These are the quotes from that early tests. First one is, for instance, L4S flows dominate non-L4S flows, whether ECN enabled or not, when they occupy a shared RFC 3168. This is the classic ECN, single queue, actually. This case is problematic. It's also listed in the early test, and it's numbered as issue number 16 in IETF meetings. And another one is the dual pi Q. This is the L4S AQM actually. QDISC introduced a network bias for TCP/PRAC flows over existing cubic flows. And another one says that TCP/PRAC behaves approximately like Neutrino and is outperformed by cubic in FIFO bottlenecks. And it is difficult to see, in this case, we can say that it's difficult to see where L4S scalable throughput claim is justified here. So these are all the three codes to just show you we have some concerns from the early test also. So also we try to evaluate these things in our experiments. We try to evaluate TCP/PRAC, a scalable congestion control, I already mentioned, with this question in mind, actually, given that bottleneck router may or may not have a dual Q AQM, this is L4S AQM, and given that the other flows sharing the same bottleneck may not be TCP/PRAC flows, what benefit can a sender expect from unilaterally switching its own congestion control to TCP/PRAC? This will be our question in this work by considering all of these things I already mentioned. We can continue with our experiment design. We did our experiments on fabric tested, and this is our topology. Here you can see we have two senders, two receivers, and we have one L4S sender, and this sender sends single TCP/PRAC flow for 60 seconds. And we have another sender for classic TCPs. It sends single classic TCP flow. I will mention this, which classic TCP flows I used for 60 seconds again. And we have L4S receiver and classic receiver. And on the middle, actually in the middle, we have delay node and to give the base RTT, and also we have bottleneck router. And we think that actually a flow is most likely to encounter a bottleneck either at the peering point or at the access link. So we try to emulate network conditions that are representative of an access link. In this case, 10 millisecond base RTT and 100 megabit per second bottleneck link capacity. We use these parameters in our experiment. We use 6 different bottleneck types in our experiments. You can see that in this table. The first one is just single FIFO. We already know that I think it's just a single queue, drop tail queue actually, it's FIFO. The second one is FIFO, but with ECN support. The third one is Codel AQM. This is an AQM and with ECN support. The fourth one is FQ. It's a fair queuing. It means that there is some flow isolation in this bottleneck, and it also has ECN support. And the fifth one is FQ Codel. It is actually similar to FQ, but with Codel AQM for each queues, for isolated queues, and also it has ACM support. And the last one is the proposed L4S AQM, dual pi 2. It has a dual queuing system, AQM and ECM support, and also it has shallow ECM marking. It has 2 queues, one for L4S, one for classic. And for L4S queue, we can apply very shallow ECM marking, such as 1 millisecond. And as I said, we use different classic TCP congestion controls. First one is cubic. It's a loss-based congestion control, and it can support ECN. The second one, we use BBR version 1. It's a rate-based one, and it doesn't have ACN support. And the third one, we use BBR version 2. It's also rate-based, and it can have classic ECN support, and also in the later versions, it can also have accurate ECN supports. And all of these classic TCPs will compete with TCP/PRAC, which is a scalable congestion control with accurate ECN in our experiments. And we can continue with our key findings. We will examine all of our key findings actually. And first one is, under what circumstances is TCP/PRAC performance at least as favorable and not harmful to classic flows? And we observe that, I can show you here. You observe that here the throughput of TCP/PRAC in these plots for different cases, and on the y-axis we can see different AQM types, bottleneck types, and on the x-axis you can see the different buffer sizes. And we can say that PRAC gets its fair share of throughput with fair queuing. Actually, it's actually a bit obvious thing. With fair queuing, we can get almost fair share for TCP/PRAC, and we just wanted to show this, to show that yes, fair queuing works very well with TCP/PRAC, actually with cubic, and also with BBR version 2 when they share the bottleneck with. And another one is under what conditions TCP/PRAC performance is not as favorable as, but still not harmful to classic flows. And I can show these conditions in our experiments, like visually here. Here we can say that with Cubic without ECN support, compete with Prague with ECN in FIFO with ECN AQM. Actually, in that case, Cubic, the flow doesn't support ECN, dominates the Prague actually. It's also a bit obvious, but here we want to show this because it can happen if any of the sender or receiver doesn't support ECN, or there is some ECM bleaching in the network. Actually, such as intermediate network device can clear the ECM flag. All of these things could happen. So this could be a problematic case if there is no ECN support with FIFO plus ECN case with classic TCP flow without ECN. There's some fairness problem. Actually, we want to show this. And also similar thing, of course, happen with also BBR version 2 here. BBR version 2 versus Prague. Also, we can observe this. And we observed another thing for dual PI2. In our experiments, we observed that BBR version 2 without ECN support competes with TCP Prague with accurate ECN on the dual PI2 AQM. Actually, this is the proposed L4S AQM. We observed that you see now the TCP Prague flow numbers. Actually, it means that BBR version 2 without ECN almost dominates the Prague with ECN, even with dual PI2 queue. Actually, we wanted to mention this. Actually, we think that it's not have been studied well. So, and this could be a problematic case because it shows that even you implement dual PI2 on the routers, there could be some problematic cases in the real networks. And another condition I want to mention, under what conditions TCP Prague performance not as favorable as, but still not harmful. Actually, this is the same condition we had previously, but now I want to emphasize the BBR version 1 instead of version 2 or Cubic. In this case, we observed that for shallow buffers, with shallow buffers, actually BBR version 1 dominates Prague in most of the AQM types, as you can see here. But this is also a listed issue for Reno and Cubic. Let's say in IMC 2019 paper from Weyer, they also shows that BBR dominates Reno or Cubic with shallow buffers. So this issue is not directly related to Prague, but it's similar issue with Reno and Cubic. We also wanted to mention this. Another thing, actually, this is the problematic case. Under what cases TCP Prague performance harmful to classic flows? It means that Prague dominates the classic flows, actually. I want to show these conditions shortly. Here, as you can see, actually, this is already a well-known issue. Cubic with classic ECN. If there's a single queue with classic ECN support, if TCP Prague competes with classic ECN with ECN, classic TCP flow with ECN support, Prague dominates the classic ones. Because of this different soft behavior, as I already mentioned in the beginning of the presentation, I showed the different behavior of classic ones and scalable ones. Because of this, because of different reactions of different TCPs, Prague dominates the other one, actually. This is a problematic case. And also we observed a similar thing for BBR version 2, Prague versus BBR version 2. We also observed that Prague with single QAQM with classic ECN support, Prague dominates BBR version 2. Also we observed same thing, Prague gets more than its fair share with also Codel with ECN, but Cubic without ECN case. In this case, we observed this because in Codel AQM, in our implementation at least, Codel dropped the packets for the flows who doesn't support ECN when it reaches the ECN threshold. So because of that, Prague dominates the Cubic flows without ECN with Codel AQM, actually. And also the similar thing happens for BBR version 2. Also, I am showing all the Cubic and version 2 results, BBR version 2 results. And also we observed that with FIFO, without any ECN support, that's single drop tail queue, we observed that Prague gets more than its fair share when competing with BBR version 2. This could be also a problematic case in terms of fairness. And to solve this single queue with classic ECN unfairness problem, as you can see in the middle part, I already showed this. This is a problematic case. To solve this, there is some option in the TCP Prague to ECM fallback heuristic, which is called fallback heuristic. In this option, it's actually optional in the TCP Prague, but it's not on by default, but we manually enabled that, and we observed that it solves almost solves this problem, fairness problem, because in this heuristic, it tries to detect the Q type and fall back, the TCP prag falls back to the classic TCP behavior. So it solves the fairness problem for single Q AQMs with classic ECN, but we also observed that it could cause some other problems. For instance, in our case, we observed that with dual Pi2, if we enable this algorithm, prag starts to get very low throughput compared to the cubic, for instance, in this case. So this optional feature can cause some other problems when it solves this main problem, actually. And also, this similar thing also happens with prag versus BBR version 2. And we can, it's the last one actually, TCP prag performance is better than classic flows. We want to see these conditions. Now we will look at the latency values here. These are not throughput, these are the queuing latency values for TCP prag. And we observe that with different AQM types and different buffer sizes and different scenarios, cubic BBR version 2, with ECN or without ECN, we observe that you can have the latency benefit only with dual Pi2 actually. It's less than 1 millisecond. Here you can see that with dual Pi2, prag have very low queuing latency because it has 1 millisecond ECN threshold for low latency queue. We can say this. And also, as I said, there's another option for BBR version 2 with accurate ECN. We also tried this. In this case, you see again queuing latency values for prag and BBR version 2 this time. In the left side, you see the values for TCP prag, and in the right side, you see the values for BBR version 2. And they compete on the same bottleneck. And in here, again, we can say that BBR version 2 accurate ECN also gets the low latency benefits of dual Pi2. You can see that the queuing latency is less than 1 millisecond for both prag and BBR version 2 with accurate ECN. So we can say that dual Pi2 works for this case also. Yeah, as a summary, we have a table. This table shows that is it okay to turn TCP prag or not. And in this table, we can say that, as I showed in the beginning of the results, with fair queuing, it doesn't depend on with ECN or without ECN. Actually, with ECN fallback off or on, actually, it's heuristic. Actually, or cubic or BBR version 2, it doesn't depend on this. We can. It's safe to turn on TCP prag because it provides fair share between the prag and the other classic TCP ones. But the other cases, it depends on the case actually. Sometimes it's not good to turn on TCP prag. Sometimes it's good in terms of fairness, of course. But we should note that, of course, the sender doesn't know what's the bottleneck type. So maybe so because of that, it might be reluctant to turn on TCP prag. We should keep in mind. And yeah, that's all actually. Thank you very much.
Thank you very much. Questions? I did see Chris asking a clarification. Don't know if Chris wants to bring it up or. With these slides, is 50 the perfect result? I think the further away from 50, the worse it's considered. I'm not really sure what he was talking about, but.
Sorry, I couldn't understand.
With these slides, is 50 the perfect result? I think the further away from 50, the worse it's considered. But anyhow, maybe Chris.
In the results, the values he mentioned, I think the values here shows the actually throughput values, so throughput percentage of TCP prag. So 50 means that it's a fair share between prag and the other TCP congestion. So in our case, we evaluate these results in terms of fairness. So 50 is the most fair case. If we say
Thank you. So we have Sylvester in the queue. Please go ahead.
Hi, I'm Sylvester from Ericsson. I have two questions. Have you considered rerunning this analysis when BBR, whether to verify whether you should introduce BBR v2? Because I think that Google is not this cautious. They just put BBR out in the wide, and it's similarly, it can create similar situations. So should the research community be this cautious with introducing a new congestion control?
Yeah, we just evaluate. Actually, yeah, with TCP prag, one TCP prag flow, one BBR version 2 flow. And yeah, of course, we need maybe further evaluations, but yeah, I have just this. And yeah, we didn't consider too much about the other version 2 case, but yeah, we have just these results for now, and yeah, we can discuss maybe later more.
And the other question is, what's your opinion about congestion control evolution in general? Is this kind of like TCP fairness, keeping TCP fairness as something we are targeting? Is this a way forward really in congestion control evolution, or should we ensure fairness in other ways? Are there really like these shared bottlenecks? Why are you considering just 2 flows and these reasonably small speeds? So is there another way to evolve congestion control and make sure fairness is solved, for example, by some other mechanism?
You say, is there another way? So, actually, yeah, I don't know for now. Actually, we just try to evaluate with these existing architectures, and yeah, I need to think about that more actually.
Because there's like less and less bottlenecks, like out in the wide in the internet, more and more in the access network. Access network can be regulated more. Even flow fairness can be maybe provided by other mechanisms than congestion control itself.
Yeah.
Thank you.
Thank you very much.
Thanks, Sylvester. And the next one in the queue is Christian. Please go ahead.
Hello, this is Christian Wiedemer. I have first a remark on the previous question. The answer on that previous question is in the draft 5043 bis, which states that we are not supposed to actually go for fairness, but you have to make sure that you don't starve the other guys. So, for example, if you end up with doing 60-40 instead of 50-50, that's probably fine. And even 75-25 will be fine. 99-1 will not be fine. That's clear. Okay. So that's just a side effect. Technical question on your measurements. I see that you are doing a lot of simulation, and that's great. That's a great spread of measurements. It's interesting. What kind of latency did you use for those simulations?
What do you mean, the base RTT? How I implement the base RTT, you mean? Or
yeah, what will be the mean RTT of the links?
Actually, yeah, we have 10 millisecond base RTT, and we implement with NetM on the Linux. These are the real experiments actually on the Fabric testbed. So we implement base delay by using the some delay node we have. We use NetM delay on this software on the Linux.
Yes.
So this shows the queuing latencies actually for TCP Prague. These are the.
So what the figures we have here are the total end-to-end latency?
No, it's a queuing latency, not end-to-end.
No.
The numbers are the absolute values for queuing latency for TCP Prague.
The queuing latency at the bottleneck, or the queuing latency at?
Actually, this is the end-to-end latency minus base RTT. Actually.
Okay.
Yeah.
Now, what would happen if your base RTT was different?
Yeah, actually, we can also measure this, but I don't believe the main messages will change.
Oh, it does.
Yeah, I mean.
Oh, it does, because the problem is that Prague specifically is based on Reno, and Reno stops operating if the BDP is too high. I mean, basically, because Reno in a congestion avoidance mode ramps up the congestion control very slowly. If it goes down, it will then take it a long time to catch up if the BDP is very high. And that's part of the range there that could be shown. I mean, if you really do same thing with 100 millisecond delay, I am concerned that you will find something very different.
You are right, but yeah, in this work we specifically focus on 10 millisecond base RTT. Actually, in other experiments we try to use 10 millisecond, 50 millisecond, 100 millisecond RTTs. Yeah. In some cases, yeah, we have some different results, but generally, we should specifically look at the different scenarios. Yeah, right. I cannot comment on generally what happens in the different RTTs. It's not easy to say that because we have different ACM types, different buffer sizes. But yeah, it's probably it's cool to be worth to look at also that scenarios. I mean, different base RTTs, we can also evaluate that. You're right. But in this work, we don't have that.
Yeah, that'd be nice to have. Thank you very much.
Thank you very much.
And my next person in the queue is Greg. Please go ahead.
Thank you for doing the study. one thing I want to point out is the 6 bottleneck types that you tested. 2 of those are not really deployed much in the internet. The FIFO with ECN and the single queue CODL. And there are a couple of other bottleneck types that might be interesting to add in place of those or in addition. So an NFQ bottleneck with a shallow threshold ECN marking. So it's basically L4S aware FQ. And the other one would be a single queue with a classic packet drop AQM. Those are commonly deployed.
Yeah, you're right. Actually, I'm aware that FQ with ECN support also available, and yeah, you're right. We can add that. Thank you very much for your comment.
And I'd like to second what Christian asked about testing other RTTs and also other rates as well, because congestion control dynamics definitely depend on the BDP of the link. So
yeah, thank you very much.
Thank you. Next person in the queue is Tianji Yang.
Yes, Kenji CMCC here. Especially for this the setup on this page, the first line, the bottleneck being shared between the Prague and the legacy flow. I remember in your architecture you have a single bottleneck. It's like only a simulated router here. Have you ever tried with the parallel paths? But that is also the bottleneck. But the one you don't know which path a legacy or LFS may go through. So have you tried something like that?
No, we just tried for now. That's just the topology. But you are right. We can use different various scenarios also. We can generate, but we haven't tried that yet.
So for this case, because sharing the same bottleneck, it might have some coordination between the the legacy and the ECN marking LFS flows. But if you have a parallel paths on the same point with the bottleneck, how can you do the coordination among the 2 parallel paths for this type of study?
Yeah, do you mean parallel pattern? Do you mean different
routers?
Different routers. Different routers.
Yeah. So
yeah, it depends on, actually, this works about where is the bottleneck. Actually, the important thing is that. So actually, it's the routing problem. I think it's a bit where it goes to flow. If the flows goes to the, actually it depends. It again depends on which AQM type will be on that on that router. So I don't know which one is with the bottleneck. So we can also figure out.
Okay, no problem.
Yeah, we haven't done it. Yeah.
Okay, sure. Thank you.
Thank you. And last question from Sylvester again.
Hi again. I was always wondering why TCP Prague is based on Reno, and how hard would it be to change it to be based on Cubic? So do you have an opinion about it? Or do you have an insight why is it still based on Reno? I know this TCP was based on Reno, but that's not a reason for Prague to be based on Reno.
Probably it's because of Reno is the most common still, or at least it started. Actually, yeah, but I mean, I think because of I don't see any some reason because of that. It can easily fall back to the Reno behavior to compete to get fairness sometimes. Actually, for instance, in the FIFO case, without any ECN support, it supports the Reno actually instead of Cubic. You are right. Cubic also could be implemented. You are right, but I don't know the exact reason actually. But it could be the inventors of this thing about that Reno is the safest one. If you want to fall back to that behavior, it would be good to have Reno in that case. I don't know actually the exact reason, but yeah.
But it still feels stupid to base it on Reno unless there is like a fundamental reason to not be able to apply Cubic.
Yeah.
Okay.
I don't know actually.
It's bugging in my mind for a while, and it was mentioned before, so I thought that maybe you have an opinion about this. Yeah, thank you.
Yeah, thank you very much.
And I said last, but it was one to the last. Alt and I had one clarification. If you can get to the microphone.
Yeah. Hi. So there is a phenomenon called ECN bleaching, where the middle devices just erase the ECN markings, and I'm wondering if you have already looked at that issue and how it affects the performance, because it's quite a prevalent issue.
Yeah, actually, we haven't checked it, but in the literature we observed that this could happen. So this could be a problematic case, but in our specific case, we haven't studied that actually. Yeah.
Okay, thanks.
Thank you.
Well, thank you very much. Let's thank the speaker for answering so many questions also. And we have now a break, and the next session will start at 3, which will be about security and energy. See you later.
Yeah, yeah.